All right, ladies and gents, physicists, let's start our first COVID physics lesson. First thing I want to do is I actually just want to start by finishing the Penny Lab that we did. You will have a document on the classroom here. This is your answers, right? Well, you have this document already. You have a hard copy, right? Has this on the other side. I'm going to give this to you, and you're going to answer these questions in the spaces provided and turn them in as your first remote assignment. I do not need to see your data here. I just want to help you with thinking about these problems. So if we take a look at level 1, data tables are completed, don't worry about it. Level 2, use your data and experience to conclude why highly ordered states are rare. If we were to roll a 5-penny system and get 4 heads up and change the system by rolling again, would we be more likely to roll 5 heads up or some combination of heads or tails? How does your answer relate to the second law of thermodynamics when stated the entropy of a system spontaneously increases? So remember, spontaneous means without thought, without intention, without your effort or thought being put into it. So why would it be more common to have a system maybe that's all heads up, we put it in the cup, we shake it up, and we spill it out, and it's probably going to come out some combination of heads and tails, right? Not all of them heads, not all of them tails, but some combo. Why? Why would that happen? You answer that question a little bit about there. Number 2, level 3 rather. Our 5-penny system was relatively simple. Only 5 pennies, each with 2 possible states, yields 32 possible outcomes. How many possible outcomes were there for a 4-penny system? Explain how you know this. What was the probability of rolling 99 heads with a 100-penny system? What can we say about the probability of obtaining a highly ordered state or a low entropy state as the complexity of the system increases? So we talked about this a little bit the day before we left, and let's just talk about what we know. We knew that for a penny system, a penny has 2 possible states, heads or tails. And to get the number of combinations, we simply raised it to the number of particles in the system. In this case, the number of pennies in the system's power. So the 3-penny system had 8 possible states, right? The 4-penny system, 2 times 2 times 2 times 2, had 16 possible states. And then finally, the last one we experimented with was the 5-penny system, 2 to the 5th. That's 32 possible states. So it stands to reason that a 100-penny system, well, pennies still have 2 states, but it's going to be 2 raised to the 100 power, a huge number. I hope you can see that. Now, the question is, we know then there's only one way to get all heads or all tails. It would be 1 out of 2 to the 100 power, right? Really, really small. The question here, though, asks, what's the probability of rolling 99 heads? So for that one, we have to look back into our data and look for a trend or a pattern. When we had a 3-penny system, to roll 1 oddball, 1 tail and 2 heads, or the opposite, there were 3 ways to do it. If we look back at our data table, if we had a 4-penny system, and to roll 1 oddball, 1 tail and the rest heads, there were 4 ways to do that. And if we had a 5-penny system, there were 5 ways to get the 1 oddball. So it stands to reason if we have a 99-penny system, there are 99 ways to get 1 oddball, 1 head up or 1 tail up and the rest the opposite. So the probability of rolling 100 pennies and 99 of them come heads up is 99 and 2 to the 100th. Right? Now, I basically did level 3 for you. This is such a huge number that 99 divided by it is a really, really, really low probability. What I want to see if you can do is, can you use that reasoning to solve this? So pennies have 2 possible states. So instead of 2 to some power, right, we could have different ones. Particles can move in a huge number of directions. The graphic below shows a piston with 10 gas molecules. Each molecule has 10 joules of kinetic energy. Answer the following. And you can write your answers down here below the caption, below the graphic. How much thermal energy is in the system? You remind yourself, what's the relationship between thermal energy and particle kinetic energy. If you desire usable work from the engine, which direction do you want the molecules to move and explain? Well, no, we want it to hit the piston and drive it forward, right? What is the probability of all the molecules moving in a direction that does usable work? So that's a probability one. You're going to look for that one, the trends of what we've been doing before. And if a molecule hits a fixed wall of the system, what happens to the energy? So let's say a molecule goes, boom, hits there. What happens to that molecule's energy? Fill out this, write your answers, your responses here, and turn it in. This will be your first formative assignment for our COVID learning, I guess we'll call it from here on out. All right, and then check the classroom tomorrow for the next step.